Welcome everybody to the new time for our regularly scheduled programming. I'm pleased to introduce Rupanjali Gurprasad today, our internal CRESP speaker. Rupanjali is a postdoctoral fellow at Georgia Institute of Technology's School of Chemical and Biomolecular Engineering, where she works with Dr. Martha Grover and Dr. Ronald Rousseau. She obtained her PhD in chemical engineering from the Indian Institute of Technology, Gandhinagar, India, in November of 2020. Her doctoral research integrated experimental and molecular simulation approaches to investigate the effect of intermolecular interactions on the polymorphism and morphology of poorly water-soluble drugs during crystallization. During her PhD studies, she was also awarded an overseas research fellowship to undertake an internship at the Agency for Science, Technology and Research, A*STAR, in Singapore. She currently serves as the outreach co-chair of the Early Career Professionals Group for CRESP. Her current work focuses on the application of process analytical technology, PAT, to aid in the control of processes related to nuclear waste, vitrification, and pharmaceutical drug crystallization. Rupanjali, the floor is yours.
Well, thank you, Steve, for that introduction.
Sure.
And also thank you all for attending my talk today. So I will be presenting our results on quantifying dense multi-component slurries using inline ATR, FTIR, and Raman spectroscopy. And it's a case study that's focused around Hanford. So to give a brief outline of the presentation, I will first, of course, start with introduction, give a little bit context about Hanford, and that will be followed by a discussion about how we are trying to help Hanford in their processing needs. So that's how we'll define the objectives of the current work. Then I will walk you all through the experimental system that we currently have at our lab here at Georgia Tech, and that will be followed by a brief discussion on the results that we have obtained so far. So to give a brief introduction about Hanford as such, so the Department of Energy, or DOE, is currently setting up a waste treatment plant at the Hanford site in Washington to remediate around 56 million gallons of nuclear waste, which were produced as an aftermath of a lot of plutonium production during World War II and Cold War. So currently these wastes are stored in around 177 underground tanks, which are also located at Hanford in Washington. So you see 12 of those tanks in this picture here. To give a brief idea of the scale, I think you can see there's a truck here. So compared to that, you can probably imagine what's the scale of the underground tanks are. Now, an issue with the current storage of the nuclear waste is because these tanks are around 50, 60 years old, they've started to develop cracks. And so the waste has actually started leaking out of those tanks, and it has started contaminating the surrounding environment, or namely especially the Columbia River. So of course it's creating environmental concerns. So to address this challenge, what DOE is doing is they are trying to convert all of this nuclear waste, and they're trying to vitrify it into glass as a long-term storage solution. So let's look at how overall the process looks like. So here is a flow sheet depicting of what the vitrification process actually looks like. So for example, this is a pre-treatment facility here where your incoming nuclear waste, which is very inhomogeneous in terms of its composition and also in terms of the solid content and everything. So it goes through a pre-treatment facility where a lot of the radionuclides are actually removed. So they remove a lot of cesium. And so you'll see a lot of those acronyms here. So if I'm not able to explain any of those, please feel free to pause and I can go ahead and explain those to you. So the law here is the low activity waste. So after the radionuclides are removed from the pre-treatment facility, the waste actually is forwarded into a different tank, which is the CRV, that is actually called the concentrate receipt vessel. So in this tank, currently, most of the waste is actually in a solution phase, so it's mostly just liquid. And from there, it is pumped and transferred to another tank, which is an MFPV, which is a melter feed preparation vessel. So in this tank, what happens is based on the composition of the incoming waste stream, a lot of solids are added to the nuclear waste. So the solids that are added are actually stored in these silos, and they are called glass forming chemicals. So these glass forming chemicals are nothing but a combination of silica, a lot of silicates, and a lot of metal oxides. So you'll see that the physical state of the waste essentially has changed. So it has gone from a solution phase to now a slurry because it has a lot of solids added to it in the form of these glass forming chemicals, which I'll be referring to as GFCs. And once that slurry is formed, it's then pumped, it is then transferred to another tank, which is the MFV. The removal of P happens, so it's the melter feed vessel. So the contents in these tanks, they act as nothing but a continuous supply to the melter, where eventually everything is heated to a very high temperature of around 1150 degrees Celsius. So everything is in the molten state. And from there, they are cooled down to glass essentially, and that's the glass then that is then taken away for long-term storage. Now, from a processing point of view, offline sampling of two tanks in this whole process is essentially required to ensure that the waste that is, the glass that is being produced at the end of the process is very durable. So the CRB here acts as the first sampling point because the addition and the composition of GFCs that is added to it kind of depends on what the composition of the waste in this current tank is. And the second sampling point actually becomes the MFPV, which is the melter feed preparation vessel. And here the sampling point is done, sampling is done to ensure that the correct amount of the GFCs have been added to the system. So currently such compositional analysis is planned to be done in an offline setup through an approach called as grab sampling. So what grab sampling means is essentially somebody is going to go physically into the system, grab a scoop of that sample and send it to lab for analysis. So there are some concerns with that approach. So the first one, of course, is a safety concern because we are exposing personnel to the waste, which is also very alkaline, and that is something that we would probably not want to do. And the second is it can also delay the downstream decision-making processes until analytical results from labs are obtained. So in this work, we are asking a very simplistic question, which is, can online monitoring techniques, for example, an in situ Raman or an FTIR probe, can that essentially be used to quantify the nuclear waste slurries? So looking at what the experimental setup in our lab looks like, so of course we have an Optimax reactor. So the reactor that we use is a Teflon material because, as I was mentioning, the waste is highly alkaline, and so we started noticing some of the degradation and etching on the glass reactor. So we switched to a Teflon reactor. We of course have a lot of in situ probes. So we have the Raman here, we have an ATR FTIR probe. Of course, there's also a pH probe, which we used to just monitor the pH during the solid additions to see if something else is happening in the system. But from what we've seen and what we've monitored so far, the pH has not necessarily changed. It always stays very basic, so it's greater than 13 at most of the times. And we've been talking about these nuclear waste slurries, so if you're wondering how that looks like, it's not a pretty picture to look at, but that's how dense these slurries look like. So it looks like a very brown, kind of a viscous, sludgy liquid. And so the one that you see here, it actually contains around 900 grams of solid per kg of solvent. So these are like highly dense, and they are highly and it's also a multi-component system. So before we started to apply these spectroscopic techniques for the nuclear waste slurry quantification, we kind of did like a quick literature review to see in what kind of application have these probes been applied to, and if there is a mention of how much amount of the suspended solids were actually present in these slurries. So this is, of course, not a very exhaustive table. I'm showing just a part of a very long table that we had. But essentially, like the takeaway from the table was that we'll see that most of the application for these spectroscopic techniques has been restricted to the pharma industry. And what we also realized was that around 12% was like the maximum solid dosage that we could find, or solid loading that we could find in these slurries. Now, a challenge with that is that the expected amount of solid content in the nuclear waste slurries that we are talking about is around 22 to 33%. So it's way higher than whatever has been seen in the literature by far. So that is then something that we decided to take forward to see and test the applicability as well as the feasibility of using such spectroscopic inline techniques for such high dense slurries. So moving forward, let's start by taking a step back and understanding the complexity of the nuclear waste itself. So if we look at the solution phase, it mostly is composed of a lot of sodium salts. So we have nitrate, nitrite, carbonate, there's some phosphate, sulfate, and all the other salts. Out of these, of course, nitrate is the ones that is a very predominant ion in the solution. So much of the research in the past in our group has focused on just quantifying these multi-component mixtures in solution phase. So a previous grad student and some previous postdocs have worked where they've looked into the Raman spectra as well as the FTIR spectra of these multi-component mixtures in solution. And what they saw was that all of the sodium salts that I was mentioning previously, they all have a very characteristic signature in the Raman as well as in the FTIR spectra. And they've shown that these in situ probes can do a very accurate job of quantifying each and every individual species in spite of it being such a multi-component system. But now eventually, so we are moving from a solution phase to a slurry phase. Excuse me. So now we'll see how the complexity of the waste essentially increases when we add these glass forming chemicals to it. So till now, before that, in the solution phase, let's say we only have 8 species that we want to be worried, we are worried about. But the moment the glass forming chemicals get added to the system, you all of a sudden transition from an 8 component to almost a 20 component system. So it gets very complicated essentially. So when we decided to do the quantification, we kind of took a call on what species were more process relevant. So for example, in the solution phase, we've looked at nitrate, nitrite, carbonate, sulfate, another anion of borate, which comes from the glass forming chemicals. And similarly, for when it comes to quantification in the solid phase, we've tried to focus our attention on silica and silicates because they actually are majority of the glass forming chemicals that's added to the system. So now before we even progress with our study, there were some of the questions that we were asking beforehand. And the first is, of course, that we want to use FTIR as well as Raman. Can we selectively use them for only solution or solid phase, or can we use both of them for solution phase and both of them for solid phase, or how was that gonna pan out? And the second question that we were asking was, how would the solution chemistry look like? Because now we're adding some solids to a very alkaline and a very basic solution. So one of the questions that we had early on was that, is there a particular component that essentially maybe dissolves, or it has some partitioning between the solution as well as the solid phase? So we wanted to be able to classify the GFC components into maybe soluble or insoluble species. So to answer the first question, where we're talking about selective applicability of FTIR or Raman for a solution or solid phase, we did a simple proof of concept experiment. So what we did here was we started with a solution that only had dissolved nitrate. The reason why we selected nitrate here is because, as I was mentioning, in the solution phase, nitrate is known to be the most abundant ion present in the solution. So to the nitrate solution, then we added a bunch of GFC solids. And we monitored what happens to the Raman as well as the IR signal of this nitrate anion in the presence of these solids. So if we look at the figure C here, what we realized was that if we were to track the nitrate Raman intensity, it actually starts to decrease with the addition of solids. Whereas if we look at the infrared absorbance, we see that it largely stays unaffected in spite of the solid loading be so high. So this simple experiment kind of made us realize that maybe we can selectively use the IR and the Raman probes, where the FTIR can be just used to probe the solution phase, and the Raman probe can then be used to probe the solid phase. So after kind of looking into this question, going back to the second question, which was about what would the solution chemistry look like? Can we actually partition off or classify the GFC components into soluble versus insoluble species? We started off by just understanding their solubility in an alkaline solution by an inductively coupled plasma spectroscopy. So these are the results from the ICP analysis. And also you'll see, so in order to simulate an alkaline environment that is there in the waste itself, we kind of simplify the system and we used a 3 molar NaOH solution instead. So what we did in this experiment was we took a couple of GFC recipes. So I think this is a good point to remind you all that all of the GFs, the gas forming chemical recipes that we have, or the simulated waste that we're working with, has been provided to us by our collaborators at Savannah River National Lab. So in this, what we did was we just suspended some of these different glass forming chemical solids in a 3 molar NaOH solution, which is an alkaline environment. And we kind of took samples out after 1 day, 4 days, 7 days, and we did this study up to a period of 10 days. And the ICP results are the ones that are shown on A and figure B. So if you see in figure A, the y-axis is actually concentration in terms of milligrams dissolved per gram of sample, whereas in B, it's actually micrograms per gram of sample. So based on the ICP analysis, we figured that there are some species that have some solubility in the waste. However, there are other species which are relatively remaining undissolved. So we could then classify some of the components into soluble as well as insoluble. So based on the ICP data, all of the 20 species were then classified into soluble, whereas the soluble component was the lithium carbonate salt. The boric acid that gets added, of course, all of it dissolves, and there is some sort of vanadium pentoxide that also dissolves in solution. The second category was the silicates, which was all silica and silicates. Now all of these compounds remained largely insoluble. But just for keeping the discussion a little simplistic, we further divided these solids into silicates as well as the metal oxides, where the metal oxides also did not show appreciable dissolution in the solution as well. So now before we embark on this research journey of trying to quantify all of these solid components, the first thing that we had to do was collect the reference spectra and see what all of these compounds actually look like in the FTIR as well as the Raman spectroscopy. So focusing on the soluble elements first, so I'll go ahead and show that. So here we have the FTIR as well as Raman spectra of the soluble components of the GFCs, which are your boric acid, lithium carbonate, and vanadium pentoxide. Now, so we see that in the FTIR spectra, there's a very strong peak at around 1640 centimeter inverse, but this is actually coming from the water. So this peak is not so that's not, the signal is not coming from any of the solid components that we've added later to the solution. It's just a water band. But apart from that, we'll see that there are a couple of other spectral signatures that are apparent both in the FTIR as well as in the Raman spectrum. So we looked a little into the literature and we realized that the boric acid, the lithium carbonate, or the vanadium pentoxide, they kind of dissociate or dissolve in an alkaline solution to give rise to a series of different anions. So we have a borate anion, we have carbonate, and we have a vanadate ion. Now we'll see that the borate ion actually has signature in the Raman as well as the IR. Similarly, we have a signature for the carbonate ion in the FTIR as well as Raman, whereas the vanadate ion is only Raman active. It's actually not IR inactive. But looking at just this data, we kind of realize that there are signature peaks and they are very characteristic of the compound that we're looking at. And that is something that we can then leverage to go back and quantify these compounds using IR as well as Raman. But because this was a solution phase, because they are dissolving in solution, we've kind of relied on more on the IR data to quantify the dissolved anions. So after looking at the soluble species, I'm going to take another case study for the silicates and kind of restrict the discussion on that. So we did a similar study with silicates by looking into their FTIR as well as their Raman spectra. So what we see here is that in the FTIR, we of course only have the water band and none of the silica or the silicates have a characteristic peak in the FTIR spectra, which is a good thing because one, it corroborates well with our ICP data, which kind of showed that the silica and the other silicates don't have enough dissolution in alkaline media to begin with. And the second good thing was that most of all the silica and all the silicates had characteristic peaks in the Raman, which kind of also tell us the same story, that we can actually use Raman to kind of quantify the solid component of these silica and silicates in a GFC mixture. One thing at this point that I would probably mention is that in case of silica and silicates, we started observing a slight fouling of our IR probes. And so fouling is essentially just like a solid deposition of the components on the probe itself. So before taking a reference for the silica or the other silicates, we made sure we always cleaned the probe before taking like a neat and a clean spectra. So of course, so from this study, we knew that the silicates have spectroscopic features in Raman, but not in IR. But I think that was a welcoming result for us, because that made us realize that we can selectively leverage Raman here again to kind of quantify the solid silica as well as the solid silicate species when we're talking about the nuclear waste slurry as a whole. So once we had the reference spectra of both the solution phase species as well as the solid phase species, the final part of the project was how accurately can we actually quantify these species in both the phases. So just to give you a brief kind of like an overview of how the spectral data actually looks like. So we have the FTIR spectra on the left, and it's a combination of all 40 and 46 experiments that we had done. And you can see that most of the process relevant anions have a very characteristic feature in the FTIR spectra. So we have the nitrate ion, the carbonate ion has a signal here, there's nitrite, sulfate, as well as borate. However, you'll see that the Raman spectra looks a little more complicated when we compare it to the IR. Firstly, we see that the signal actually has a lot of fluorescence because of the added solids. And the amount of peaks that we see in the Raman, they're not as clearly visible or clearly evident as compared to the IR spectra. So we were a little skeptical in terms of how good or bad the quantification would look like. But let's just, so let me go forward and show you how the quantification then looked like. So first is the quantification of the solution phase using ATR FTIR spectroscopy. So here, what I'm showing are a lot of parity plots, which have the predicted molality of concentration of the anion on the y-axis versus the experimentally measured molality on the x-axis. All the different plots are for different anions. So we have nitrate, nitrite, carbonate, sulfate, as well as borate. A couple of features about the plot that are important to know are, so the black solid lines on the plots are actually, they show an ideal predictive model. So it's like a y equals to x kind of correspondence between our predicted versus measured concentrations, where that is an ideal case, or we would want our predictions to lie as close to that line possible. We are also comparing our results to these plus and minus 20% accuracy bounds, which are shown by these dashed, broken dashed lines on both sides of the curve. So these bounds that you see are actually coming from our knowledge of the accuracy that's reported of these offline lab analysis. So ideally, we wanted our predictions to lie within these bounds, because we're trying to kind of see if an online monitoring approach can actually complement the offline analysis. So if the accuracy is still within those bounds, it would be like a good and a hopeful win for all of us. So based on the FTIR results, we see that the solution phase quantification was actually very accurate for most of the anions. We had an R-square value greater than 0.99, except for sulfate, which was around 0.96. And a potential reason here is that firstly, the amount of sulfate in the waste essentially is very on the lower side. Like if you look at the axis here, it's going from 0 to around 0.12, whereas for the other solids is a little higher than that. And the second is also the IR peak of sulfate ion is also not as prominent as the other anions. So that are two factors that we think are responsible for not bad, but a slightly lower accuracy as compared to the other ions. So this kind of also shows us that the IR is actually doing a very good job in predicting the solution phase composition in spite of having a solid loading of as high as around 23.88%. When we look at the results for Raman, so for Raman, as I was mentioning, we initially focused all our attention on quantifying the main components in the solid, so which was silica and the other silicates. So the results are, of course, not as accurate as what we had gotten for the solution phase in the IR spectra. But that being said, they are also not that bad. I would say like they are semi-accurate, where we still have good enough predictions for silica, zircon, which is zirconium silicate, and all the other silicates in the solid phase. One of like a bad or like a lower prediction is something that we're getting on olivine, which is magnesium sulfate, and the predictions seem to look all over the place. Again, so for that, we think it's one of the reasons is probably because the amount of olivine that we had used in our training and testing data was not that high. And the second thing is, again, of course, the olivine also has like its feature in Raman is not very prominent. So both of those reasons coupled together could lead to a poor quantification of olivine. But that being said, so currently in the group now, so all of these quantifications were done using a partial linear square regression model. But there are a couple of group members who are now also looking into see if maybe nonlinear models would do a better job at giving us better prediction accuracies for the Raman as well as the IR data having such a high amount of solid content. So to summarize, what we've shown is or demonstrated is that the NC2ATR, FTIR, and Raman spectroscopies, they both can be applied to obtain an acceptable quantification of these highly dense and highly multi-component nuclear-based slurries. So with that, I would like to acknowledge both my supervisors, Dr. Grover and Dr. Rousseau. Huge shout out to the grad student, Stephen, for his help in all of this work. Of course, we are thankful to CRESP for their funding, and our huge thanks to our collaborators at Savannah River National Lab as well for their help in sending us all the simulants as well as the glass forming chemicals. So thank you. And with that, I would be happy to take any questions from the audience.
Thank you, Rupanjali. I believe we have our first question already.
Oh, okay. Wait, I cannot. I hate when Teams does this. Okay, I'm going to come here and then go back. Yeah, hi. I see a question by Dr. Gruber.
Hi, thank you for the presentation. My question is, I was quite surprised to see kyanite in the solids. Kyanite is a mineral that forms under very, very high pressure in natural environments. How do you explain the presence of kyanite in this system without significant pressure? Do you have an independent evidence for this mineral? And the second question regarding the olivine, olivine has solid solution with substitution of magnesium with iron. Is that possibly explain the variability in the prediction?
Okay, so like to answer your first question, or I think that takes like the second question as well. So like the solids that we are using or that we've tested in our systems, I don't think they've formed as a result of any chemical reaction as such during their addition. So kyanite, for example, that is something that we are inherently, it has been added to the system externally. Like it's not something like we synthesize during the mixing of the solid with the liquid. So like I'm not sure, like I'm not sure about the pressure sensitivity of kyanite itself. But we've done some measurements with Raman and XRD, and we've seen that kyanite remained as kyanite even before and after our measurements. And the second one also, I think, because like I don't we've not seen like a chemical change as such happen in our system. So I'm not sure if any of the change in the state because of a magnesium or an iron would actually happen. If that answers the second part as well.
Yes, thank you.
Mhm.
Any others? Going once? Going twice? Alrighty. Well, thank you so much again, Rupanjali. It was an excellent start to our 2023-24 year. And I would also like to thank everybody else for attending. We will see you in, I believe, 2 weeks. Correct me if I'm wrong. And until then, even though it's Thursday, I'd like to wish you all a lovely weekend and take care.
Thank you, Rupanjali.
Thank you.
Thank
Bye,
you.
everyone.
Thank you.
Thank you.